Thanks very much for the invitation. It's very nice to be here. So I'm going to talk about Polymatrix games today. I don't assume much. So let me tell you what they are. These are many-player games. For us, they're going to be graphical games, meaning there's an interaction graph that's going to specify who interacts with who. In that graph, the nodes correspond to players, so every node is a player, and edges correspond to bimatrix games between the two endpoints. So in that sense, these are modeling pairwise interactions. The way these are played is, each player, each node, picks a single strategy that they play in all the bimatrix games of the edges adjacent to them, and then they receive the sum of the payoffs of all those bimatrix games as their total payoff, which is what they're trying to maximize. So they were first introduced a long while ago in 1968, and I'm going to touch today on both a bunch of classical work on polymatrix games and some more recent work. There's been a bit of a resurgence. So I'm going to touch on classical work of Eves and Hausen from the Lemke algorithm you may have heard of in the 70s. And then I'm going to touch on some work of others more recently, including Ruta, who's here, Aviad, who's here, some work of John Fernley and myself and others. John's here. My goal is to kind of present some algorithms, some open problems, and kind of some applications. So how convincing you find the applications is another story. So formally, we have n players. Each player has a finite pure strategy set, and payoff matrices for player I, we're going to denote as A, I, J. So player I has, in the complete case, has a payoff matrix A, I, J for all J not equal to I. And in some of our reductions, we're just going to assume a complete interaction graph where if there isn't an edge, you just put zeros for the payoffs for those missing things. Okay, and then given a mixed strategy profile, so so xi is now a mixed probability distribution over the pure strategies si. We have one of these for each player. Then the expected payoff of player I is just this sum here. So he plays this xi in each of the bimatrix games, and gets what is expected against xj for each of the other players.
I guess someone stops
Maybe. It's like in the xj. Yeah. Correct it as you see fit. You'll almost certainly be correct. Okay, so here's a simple example, which we're going to come back to later. As you see, these particular bimatrix games are stuck in these edges, have a very particular form that we're going to use later. So here we have a complete graph. We have players 1, 2, and 3. They play these bimatrix games. Player 1 has to have the same number of strategies in all his games. Player 2 has to have the same number in all of hers, but these do not need to be the same number, but they are in this case. And if we look at the special form here, we see that actually somehow we're picking up payoffs according to cuts in the graph. So essentially, you'll see that if you can think of A as being, one part of a partition of the nodes into two parts, B being the other part, and then we pick up the payoff between, say, 1 and 3, if 1 and 3 are in different parts of this partition. So we're going to come back to this later, and then hopefully it's not too hard, or I can easily convince you that it's a Nash equilibrium for 2 to be on her own, meaning choosing A where the other 2 choose B, or choosing A where the other 2 choose B, or vice versa. Okay, because then we pick up these 2 big payoffs too, and if everyone picks the same, then no one's getting anything. That's obviously no good. And if we have some other configuration, then there's an incentive for the person to jump over so that 2's on their own. We also have this rather uninteresting mixed equilibrium where people mix half-half between A and B. And that's an equilibrium because if your two opponents, the two other people you're playing with, are randomizing uniformly, then you're indifferent between your strategies.
So B2 is always to choose B, or or these are all the equilibria?
These are all the equilibria. Two pure, one mixed, the two pure kind of equivalent in a sense.
So for the top matrix, for example, the top matrix says that so the payoffs in red are the ones corresponding to player 1, the payoffs in blue are the ones.
Well, that's not quite clear in general if I depicted a general game like this, but because of the symmetry, it doesn't matter in this example. Okay, so what's a clear advantage of polymatrix games? If you have a general number of players, a strategic form game will be exponential in size. A polymatrix game, on the other hand, is polynomial in size. So for a general strategic form game, if we assume for simplicity in this calculation that each player has exactly k actions, then we need to specify payoffs for each of the player for each possible choice of among their k actions. So that gives us this n times k to the n, many payoffs that we need to specify. In a polymatrix game like this, on the other hand, we have the n choose two edges. These are the bimatrix games, and in each bimatrix game we have k-squared cells and two payoffs to specify. Okay, so we have this succinctness, which means that we can actually write down many player games and actually reason about them, whereas for a strategic form game that would be very hard to do. Okay, so sorry. Okay, yeah. So application-wise, so I'd like to claim, as I was just doing so, that they can be useful as a general modelling tool for multiplayer games. But we'll also discuss a couple of applications that have appeared in the literature. The top two are rather similar, and we'll come back to those. That is a relaxation labeling problem for artificial neural networks and a graph transduction problem in machine learning. Also to model two-player Bayesian games, which we'll come back to at the end, and also as a subroutine for solving general multiplayer games. So if you have a general strategic form game, Davidian and Wilson gave an algorithm that iteratively approximates equilibria in the general game using a sequence of polymatrix games. Okay, so the take-home message from this talk, one of them at least, should be that many of the things that I consider to be nice, at least, about bimatrix games carry over to polymatrix games. The rational equilibria, formulation as a linear complementarity problem in a very simple way that we'll describe. A direct applicability of complementary pivoting algorithms like Lemke, Hausdorff, and Lemke. And we'll touch on an approximation algorithm that is the best in terms of the approximation guarantee, polynomial time algorithm for bimatrix games, where the idea extends to polymatrix games. That's actually the only bit of my own work that I'll present in the talk. The rest is kind of classical or other people's recent work. There are also important differences, and so there are two important complexity classes that everyone interested in computing equilibria should know about, at least. One is PPAD, another is PLS, and actually polymatrix games can capture the hardness of both of these classes. So the example that we already saw is already useful for showing that finding a pure equilibrium of polymatrix game through PLS hard. And Aviad proved that it's PPAD hard to find an epsilon Nash equilibrium in a polymatrix game for a constant epsilon even. And I'll come back to contrasting that with bimatrix games a bit later. Okay, then, so the outline for the rest of the talk, I want to tell you what a linear complementarity problem is, because I think these are good things to know about. I'll then present the Lemke-Hausen algorithm for bimatrix games, where I think that's nice because it immediately gives a nice introduction to the complexity class PPAD. So then I'll actually present a reduction from a polymatrix game to Lemke LCP. Well, anyway, is it an LCP to which Lemke's algorithm can be applied? Lemke's algorithm is similar to the Lemke-Hausen algorithm. I won't really go into the differences too much, but you'll get the flavour. And then I'll talk about some of these Polymatrix games that lie in the intersection of PPAD and PLS. So I'll introduce PLS. Then we'll talk about this descent method that I mentioned for approximate equilibria. Everything before that will have been about exact equilibria. And then I'll talk about some other recent work, including, I'll mention Guido's work, which he's about to present after the break, due to some nice scheduling. Okay, so what's a linear complementarity problem? So the data of the problem is a square matrix M, and in dimension n, and an n vector q. Okay, so the data is qm, and we're asked to find these two n vectors z and w, such that w satisfies this, this linear constraint here, and is non-negative, and z is also non-negative, and then we have the complementarity condition, which we show like this, which says that the dot product of these two is 0, which, since they're both non-negative, implies that component-wise, for each of these pairs, zi, wi, at least one of them must be 0. Okay then, so it's worth, in fact, it's more important to note this for the actual exposition of Lemke's algorithm, I guess, but anyway, it's worth noting that if Q is non-negative, we immediately have a trivial solution to the LCP. So if Q is already non-negative, we can set Z to be 0. Q is non-negative, so W is non-negative. And because we've set Z equal to 0, we satisfy all the complementarity conditions. And actually, that's a way that you use that kind of idea in Lemke's algorithm to initialize it. Okay, so let's just see how we can, how LCP, the complementarity problem generalizes linear programming, and we'll use this again, this idea again of encoding complementary slackness when we come to the reduction from Polymatrix games. So we have LPs in standard inequality form here, the primal dual pair, and we immediately get, just by looking at the inequalities in the constraints, we immediately get weak duality, which is that the objective function values are bound to each other. But then strong duality, which is a non-trivial result, gives us that we have these feasible primal and dual points. Then we have equal objective function values for optimal primal and dual solutions. Okay, so using strong duality, we can write down complementary slackness. It comes directly from strong duality, and that is exactly complementarity conditions like the following, where again we have non-negativity of these two parts, which give us this component-wise property where one is strictly satisfied, then the other must be equal, or it must be binding. And so we're going to write down a linear complementarity problem where now you should look at these two parts that we got from these two parts here, and we've encoded them in the two rows, okay, the two parts of the LCC. So for example, here we see that we have X is non-negative and complementary to exactly this thing. Okay, any questions at this stage? Okay, so now let's see one more example of encoding a problem as an LCP. So now we're going to look at the problem of symmetric equilibria of symmetric bimatrix games. So these happen to be as general as n-line games, which we can see by a relatively simple reduction I won't go into the details of. So now a symmetric game has the property that the payoff matrix of player 2, say B, is equal to the transpose of A, the payoff matrix of player 1. So it's symmetric in the sense that you can exchange the players and not change the game. So now, when is a mixed strategy a best response? Well, a characterization of a mixed strategy being a best response is you only assign positive probability within that mixed strategy to things that are pure best responses. Okay? So a way to write that down is, if some component of your mixed strategy is positive, then the corresponding pure strategy must be a best response, and that is exactly going to be encoded as the complementarity condition in an LCP. Okay, so against mixed strategy Y. AY gives the payoffs that player 1 expects for the rows. Okay, so AY1, the first component, is what player 1 expects for his first row. And so now X is the best response to Y, as we know, if X maximizes the expected payoff, which is equivalent to, for all I, if Xi is positive, then AYI must be equal to the max over all of those components of AY. And now we can write this down as a linear complementarity problem. What we're going to do is, we're going to assume without loss of generality that A is positive. We can just add constants to make this so, which then implies that the payoff we get, this U here, this best response payoff, is always going to be positive. And that allows us to actually, well, we'll see this corresponds to objective transformation. It allows us to divide through by U, do a change of variables, and then we get this very nice simple form of an LCP which captures the bimatrix game problem. So here we just have Z non-negative, a positive matrix A, and the constraint that A, Z less than or equal to 1, and the complementarity condition. Okay, so Z is in an equilibrium. It won't in general be a probability distribution, but to get back an actual equilibrium, you just normalize it. You just sum up the entries and divide them.
One question, the U, you treat it here as a parameter, but U is a function of Y, isn't it? If you go one slide back.
Yes, U of course U does depend on Y, that's true. But as you'll see, what we're really doing here, let me go to a picture. What we're actually doing here is we have some best response polyhedron, where you see here we have U as a variable that defines this polyhedron. It's a single variable, and that gives us a polyhedron where essentially for any mixture Y, okay, seems to swap to X here, but okay, so for any mixture that the column player plays, what this polyhedron is encoding is what is the best response of the other player. So, you know, if we're over to this side of this point, it's uniquely 1, it's uniquely the first row. If we're over to this side, it's uniquely 2. And if and only if we're exactly at this 2/3, 1/3, we get that the payoffs of these two rows are equal and we can mix. Okay, what's this projective transformation correspond to? It corresponds essentially to looking at this polyhedron from 0 and intersecting with U equal to 1. Okay, combinatorially, we keep all the information along this upper envelope that we're interested in. One thing that we gain is, as a projection from infinity, we gain the origin as a new point in our polytope, which we've got from a polyhedron. Actually, the origin is going to be the starting point of the Lemke algorithm that we'll see in a minute.
So the U is not disappearing, it is encoded now in the sum of the x's, because that was constant y, now it's 1 over this. So we don't lose information, because x is now
exactly
no longer...
Yeah, so this holds. This equation here.
We throw away the constraint that the x's sum up to 1.
Okay, so now we have a polytope instead of a polyhedron, and so I've now jumped up a dimension. You haven't seen the matrix corresponding to this, but assume we created this thing in the same way. There's one thing I need to tell you though about these labels. So that is the blue labels I've already described. They're telling you for a particular mixture what are the best responses. So at this point we have label 1, which says 1 is the best response. At this vertex we have labels 1 and 2, which says both are the best responses. We've also labeled these side facets, and the interpretation of them is the following. They are actually corresponding to the player whose mixed strategies we're looking at best responses against. So here, this 1 is actually signifying that x1 is equal to 0. Okay, and what this gives us is, this gives us a reinterpretation of that characterization of equilibria in terms of the complementarity condition as completely labelled pairs in these polytopes, essentially. So now at equilibrium, we have an equilibrium if and only if we have a vertex, or actually it doesn't have to be a vertex in a degenerate case, we have a point here that has all labels. A pure one would be, say, a 1 here, meaning we don't play strategy 1, and if this was a 2, then this would be completely labelled. That would be a pure equilibrium where we're not playing 1, but we're playing 2, which is the best response. Okay then, so then we're ready to look at the symmetric Lemke-Hausen algorithm. This point here, so the red labels are corresponding to the mixed strategies which we look at best responses against. So these are corresponding to strategies played with 0 probability. The origin is this extra point that we've got as a projection from infinity, and these here are the best response labels. We start from the origin, and note that the origin has all labels, but it's not actually an equilibrium. We can't normalize it and get back a probability distribution, but it has all labels, and so the way the Lemke-Hausen algorithm is going to work is we're going to pick a label, and that label is going to be missing throughout the computation. We pick this label and we drop it in the sense that we relax an equation that gives us the freedom to walk along an edge. In this example, we're going to drop label 1, which means we can walk away from the back. When we walk away from the back, at the end of this edge, we pick up another label. Either that label is the one we dropped, or because we started with a completely labelled thing, it's a duplicate. We now have a label that appears twice. In this case, it's not the missing label 1, it's 3 that we picked up, so now 3 is duplicate. We have 3 both coming from this blue 3 and the red 3, which is the bottom of this thing. So now what we're going to do is, you can probably imagine, we're going to drop the red 3 and we're going to go up like this. And again, we either pick up 1 or we pick up another duplicate. We pick up 2, go, whoops, we go away from 2, which was this left side, so we go away from the left, picking up 3 on the bottom, now leaving the blue 3, and finally we're done. We've picked up 1 missing label. So this is how Lemke-Hausen works, and let's just go over the argument that this is going to terminate. So we have finitely many vertices in this polytope. There's always a unique starting edge given the missing label. Okay, so we have a completely labelled origin. We drop a label that gives us a unique edge to go along. And likewise, when we get to a new vertex, when we pick something up, it gives us a unique edge to go along. At a particular vertex, we have these 2 missing labels. Dropping one of them goes forwards on the path, dropping the other one goes backwards along the path. So that precludes having a cycle, and therefore, eventually, we must terminate with an equilibrium. Okay, so any questions on Lemke-Hausen? So if you've got the basic spirit of that, then we can talk about the complexity class PPAD. So we basically have a graph here with degree at most 1, a directed graph with degree at most 1, and we're given a source in this graph. So we're given, say, this red vertex here. So because it's a degree at most 1, it's a collection of paths and cycles. And our goal is to find another source or sink. Okay, so one way we can do this is to start at the point we're given, the red node, and just walk along this path and get to this blue one. Okay, if you were given this graph explicitly, then this is obviously an easy problem. But the catch is you're not. This graph is given to us, this exponentially large graph is given to us by 2 Boolean circuits, S and P. So these are defined on bit strings of length n. Okay, so here, the start vertex is the all 0 vector, all 0 bit string. And the way we check whether an edge exists or not is we compute S of a bit string. Okay, in this case it gives us 0, 1, 0, 1. And now we check if P, which stands for predecessor, S stands for successor, we check if P of S of the bit string is equal to that bit string. Okay? Only if that's true do we actually have an edge there. So in particular, at these endpoints, that's not true, and we're looking for such bit strings. Okay.
So it's actually 16 nodes from you.
That's probably an accident, but anyway. Yeah. Okay, so I don't recall that. Okay, so a problem is in PPAD if it's reducible in polynomial time to this problem end of line, and is PPAD complete if also we can reduce end of line to it. It's worth noting that this should not be confused with other end of this line, which is the problem of actually finding this particular blue vertex that you get by walking along the line that starts at the point you were given. That's actually a p-space hard problem, and that's been used to prove results like for this Lemke-Hausen algorithm. It's p-space hard to find any of the equilibria that you might find at the end of these Lemke-Hausen paths from the artificial equilibrium. Okay, so in the seminal work of Daskalakis, Goldberg, Papadimitriou, Chen and Deng, and extensions with Teng, they showed that PPAD complete to compute an exact Nash equilibrium of a bimatrix game, and therefore a polymatrix game, because it's just a bimatrix game on a single edge. Later, we're going to talk about PPAD-hardness results for approximate equilibrium. So I'm not really going to talk much about how hard we think PPAD is, but we do not believe, well, I don't know anybody that believes that there are polynomial time algorithms for PPAD hard problems. Okay, so now let's look at a reduction from polymatrix games to Lemke LCPs. So there's at least three in the literature. One by Hausen, a more general construction by Eves, and something by Miller and Zucker in the 90s. What I'm actually going to present here instead is something that I found in Reuter's thesis. So if you have questions on it, just ask Reuter. And which actually, I think she was motivated by some work with Bernard that I'll talk about in a minute. But it turns out this is actually a specialization of this general thing that Eves had in his paper. So it can be shown, yeah.
It was in a paper with Jugal and Albertian.
Okay. Where was that? That was a wine paper. Okay, yeah, okay, good. So it was joint work with Jugal, who's here, and Albert Jan, who also works on equilibrium computation works. Okay, so, and the reason I want to present this instead of something that may, in some sense, be simpler, because it's just for polymatrix games, is these bilinear games, they also capture the sequence form for extensive form games of Bernard. They're quite easy to understand, so I think they're a good thing to know. I think it's a good way to think about these. And also they look, as you'll see in a minute, they look like bimatrix games with an obvious generalization in the constraints of what strategies people can play. So anyway, so as I said, inspired by the sequence form of Kolomogidou von Stengel, Nimrod's also here, as well as Bernard. So these are for extensive form games. So these are games on, these are the type of games that Kusha was talking about yesterday. So there are two players in these games. The difference is we have general polytopic strategy constraint sets. So, okay, so again we have two n by n dimensional payoff matrices, A and B. Okay, so the two payoff matrices, the same dimension. The difference here is we now have these strategy sets. So player 1 has to play a strategy from X, player 2 from Y, where before these were just simplices. These were just all mixtures over a finite set of pure strategies. Now these can be more complicated things. Okay, so the payoffs are, as we've seen, XTAY, XTBY, as for a bimatrix game. And the Nash equilibrium condition is exactly what you'd expect. The only difference here is, these X and Y are not what we've seen so far. They're not simplices anymore. Okay, so the way we're going to get an LCP is actually we're going to write down the best response condition for one player as an LP. We're going to take the joule and we're going to encode these in complementary slackness. So we've kind of already seen that. Here, this is in inequality form, and this is actually, I think, this is exactly how it was written down in Bernard and Nimrod's original paper. Okay, and so what we're doing is we have this non-negativity of x. So the such-that row is just saying that x is in x. And then against the given y, we're just maximizing the expected payoff of player 1 by choosing an x that satisfies the constraints. We take the dual LP, and then we're going to write down using strong duality. We're going to write down, okay, so this is strong duality. Okay, something that's fuzzy. This is strong duality, and we are going to get from that complementary slackness. So we have non-negativity of these two terms, and we have that their dot product is equal to 0. Okay, so I now show you what the LCP looks like, and I'm just going to flip back to this and hopefully convince you that the first row is exactly encoding this thing. Okay, so one thing to note is in these dual, in the dual of this best response LP, P and Q were unconstrained now, they're not non-negative. So we get the standard thing, and we can split them into two parts, P prime, P double prime, and that's why in this first row, we actually have both ET and minus ET. That's corresponding to this P prime and P double prime. Okay, and now you should think of this Z going that way, and this first row is going to be complementary with the X. And now you should see what's multiplying what here. Imagine this Z above here, and we see that we're getting minus AY, ET, P prime, and so on, which together that complementarity is going to correspond exactly to this thing here. Okay, so the main story is that there is a relatively nice, easy way to write down these bilinear games as an LCP. It captures both the sequence form and it captures polymatrix games, and obviously thus bimatrix games too. And then, I mean, I'm not going to go into any of the details here. So basically, as Ilan mentioned in his lightning talk, lots and lots of research into the linear complementarity problem was about when Lemke's algorithm would terminate for certain types of matrices. Here we have a condition, so the Miller and Zucker reduction from these three reductions I mentioned, what they do is they give a reduction and show that the M that you end up with is called co-positive plus, and that means that this thing is going to terminate, and that condition does not then depend on the Q. Here we have a condition taken straight from Bernard and Nimrod's paper, which in turn was extracted from the Bible of these things, a book of Cottle, Payne and Stone, which basically does depend on the Q, but says if we have these conditions, Lemke's algorithm is going to work. And so once we have this, we just can kind of forget about it. And for bilinear games, Lemke's algorithm is going to work. And so the final thing I show on for this part of the talk is that, and you'll see there's some redundancy here, where you actually end up taking a polymatrix game to a bilinear game. So it's maybe not the most succinct reduction, but it's a nice one nonetheless, where we now end up with a symmetric bilinear game, and now you should be looking row-wise that along this row, player 1 doesn't play with himself, but plays with all the other players, and now the constraint sets are just requiring that we have mixed strategies for each of the players, essentially. Okay, so one remark is that existing reductions like this essentially are assuming complete interaction graphs. If we were missing some edges, then we would just be filling these in with zero payoffs. It's worth noting, Aviad's result, that I'll talk a bit more about later, actually produces games that are degree 3 and bipartite, right? So, I'm not claiming here that there's necessarily theoretical open problems here, but it might be nice to think about, if you actually want to solve polymatrix games, how you can do things when you actually have non-complete graphs with many edges missing, how you can actually write these down and solve them in better ways than maybe these reductions I showed you. Another is a recent result that we'll come back to in the approximation part in a couple of minutes, is that we now have a QP test for polymatrix games on trees. So one could consider other graph restrictions on the graph, perhaps. Okay, then,
So here, the single edge would also be a tree. So that's the same story?
yes, but we do already have a QP test, Lipton-Markakis meta for bimatrix games, and this extends it to polymatrix games with trees, with also using dynamic programming. Okay, so now my kind of an open problem I'm fond of, and one of the applications relates to these polymatrix coordination games. So that's why I put this in here, mainly to present this open problem, but also to alert people to this application that's been in the literature and see what people think of it. So let me just quickly say what PLS is. So PLS is about local search. So we're given 3 algorithms. So whereas we had this implicit graph with degree at most 1 in the case of PPAD, with PLS we have implicitly this DAG basically. And we're given a starting solution, so this DAG is exponentially large because the solution space corresponds to all bit streams over a finite alphabet, so this is exponentially large, and we're given 3 polynomial time algorithms, one that gives us a starting point, so that's the S here, another one that computes a neighbouring solution whose cost is no greater, is smaller than the current one, strictly smaller, or reports that no such thing exists. That's what gives us the DAG structure. And our goal is to find a local optimum of the cost function. So whereas in PPAD, the underlying combinatorial principle that ensured that we had a solution is if you have this degree 1 directed graph and you have a source, you must have a sink. Here, basically, every DAG has a sink is the underlying combinatorial principle. So we can just start, we can follow this this function that tells us where we can go next and improve our cost, and in the end, we get somewhere. In general, following this is p-space hard for PLS complete problems. And so one of the most natural...
So which question is p-space hard?
To find the solution that you get by actually following this this function that gives you the next...
So the DAG is, implicit because it's decreasing, so it's
yes, exactly. Yeah. Okay, so I started a couple of minutes late, didn't I? Good. So okay, so anyway, so we actually already saw this reduction basically. So I would argue, maybe Martin would agree because we were discussing this at some point. We did one of these master reductions from PLS to some problem, not very pleasant. These are really long involved reductions, but actually many simpler reductions can start from local max cuts. Okay, so circuit flip is kind of a canonical PLS complete problem. Schaefer and Yanakakis wrote a very nice paper that reduced circuit flip to local max cut showing that PLS complete. I won't go into the details, but I'll show you how we can go from local max cut to a polymatrix game. And so you should think of local max cut, actually I haven't told you what it is, but you should think of it as being to PLS what maybe 3 says to NP. A very useful starting problem to reduce from. So local max cut is the name I'm using for max cut with the flip neighborhood, where what that means is, so one of our candidate solutions, our solution space, is all partitions of a weighted graph into 2 sets, the left and right side of the cut, and now the flip neighborhood says exactly one node can jump over to the other side. Okay? And so now the local solution to this is one where no node can jump over and improve the cost or reward of the cut, however you define it. Okay, and so just I won't go through the example, but of course, the actual max cut is one of these local max cuts, but we can actually have other ones too. Okay, I don't think I think it's quite believable, so I won't go through the example because I want to get through some of the other stuff. So anyway, we already saw We already basically saw this reduction. If we take an input graph like this, an instance of local max cut, all we basically do is we create these, we keep exactly the same graph as the interaction graph in the Polymatrix game. It wouldn't need to be a complete one. And we replace the weights with bimatrix games, 2x2 bimatrix games, where the weight appears for both players on the off diagonal. And it's exactly doing what we want. You're picking up based on your choices. So the choices of each player choose either A or B, but some of them on the A side, some of them on the B side, and then essentially they're getting, you're encoding the value of the cut. And the basic way okay, so when I say a team polymatrix game, also called a polymatrix coordination game, the restriction here is that A equals B. It doesn't restrict what happened on the diagonal, off the diagonal, just that A equals B. Those turn out to be potential games and therefore in PLS. These are particular ones that encode max cuts. The basic argument for all of these is that you can define a potential function where you sum up what each player gets for a given strategy profile and divide that by 2. And that's going to be an exact potential function, which means the following. When a player I changes its strategy, then the potential function value will change by exactly I's changing utility. Hence the division by 2, because when a player changes, their own payoff changes, but also the person on the other end of that edge changes too. So if you just sum up the utilities of everyone, you're getting this change twice, and dividing by 2 corrects and makes an exact potential function.
But the team definition applies only for the involved players, not the zero players, and then just or does it make sense? I mean, team means everybody gets the same payoff.
In that game, well, I mean, the zero, both players get 0, that's also team, but I mean, I'm not sure what your question is.
Oh, it's not team across.
No, it's a local property.
Yeah.
It's team in the sense that we discussed the bimatrix game. Yes,
for the bimatrix game.
Bimatrix.
So as a bimatrix game, it's not a team game. It's only locally a team story. Yeah.
Correct. Yes. Okay, so I mean, in exact potential games, it's not hard to see that the pure equilibria exactly corresponds to the local optimum of this exact potential function, and our potential function value equals the value of the max cut for all strategy profiles. So this is a valid reduction. We've actually shown that finding a pure equilibrium in a polymatrix game is PLS hard. And so now okay, so this is in contrast to bimatrix games. And next, an application of these team polymatrix games. So this is called graph transduction. It's a semi-supervised learning problem where our goal is to estimate a classification function. So we're given a graph, and you should think of the nodes as data points. Some of them are given labels. We're told that they're from a particular class, and we have other unlabeled nodes. In addition, so our goal is to propagate the labels to unlabeled nodes in a consistent way, and the information we're given to decide what is a good way to do this is we're given weights where edge weights represent similarities between the two nodes. Okay? So one approach is to use global optimization, and there's a bunch of ICML NIPS type papers that do graph Laplacian regularization and various other global approaches. An alternative in the literature is to use a polymatrix game. So I noticed if you didn't have the labels, if you didn't have the ones where you were given a class for them, an actual label, this would be like a clustering problem.
What are these labels? Something numbers?
So think of a finite set of classes. In a classification problem with 2 classes, it might be spam and not spam. But now imagine you have 20 of these classes. Okay, and so in terms of clustering, I just want to refer to a paper on hedonic clustering games, because there are these hedonic games that you're going to hear about elsewhere in this workshop, where essentially the pure equilibrium polymatrix games can be thought of in the context of hedonic games. And there's a paper that exactly does clustering, so closely related to this approach, but where you're not given some labeled examples. You can think of these labeled examples in a polymatrix game as just being things that only get a payoff by playing a particular thing or only have one strategy. You can easily encode that. And now, essentially, you can think of this as rather than having zeros on the diagonal, we're just going to have zeros off the diagonal and pick up things for where we agree with our neighbours. And now the question is, what should we decide to do so that we can kind of maximise with respect to, the potential disagreements, because people similarities don't exactly agree, and we're looking for local optima. Of course, maybe what we're really interested in is the global optimum of the potential function. That's an NP-hard problem. So perhaps the local approach does make sense. You can, for example, start from a whole bunch of points, do local improvements, maybe take the best in terms of the potential function value, if that's actually a good predictor of how good the classification is. And there's some empirical work on this. As a kind of pseudo-motivation for this open problem I'm about to give next, it has separate kind of theoretical interest. People also looked at asymmetric similarity. So then it's not necessarily a potential game, you may not have a pure equilibrium, but then you'll always have a mixed equilibrium, and you can think of that mixed equilibrium as giving you some kind of fractional classification. Okay, so anyway, open problem. Can we compute a mixed Nash equilibrium of a team polymatrix game, or called by Daskalakis and Papadimitriou a network coordination game in polynomial time? Or can we show this is hard for some natural complexity class strictly inside PPAD and PLS? So this problem is in PPAD, as we discussed, so by Lemke's algorithm or fixed point arguments. It's in PLS because we can do local improvements on that potential function I showed you. It's unlikely to be hard for either of them, because if it's hard for one of them, then that puts that one inside the other one.
And why this is unlikely?
Do you believe PPADs in,
No. Some results like a PPAD, not an NP complete, say if it's true that something else that is horrendous. It's not true, it does something like that.
No, there's nothing too horrendous, but it would be a quite amazing thing, I think, nonetheless.
There are oracle situations, for example.
Okay, so there is some consequences.
There is some evidence.
Very, very surprising out of it. So if somebody proved that, there will be surprises. Not by itself.
It wouldn't be like it's not like surprise like the polynomial time hierarchy collapsing, but it would still be sufficiently
I
surprising.
ask something more specific. There are some problems in which if the statement is true, then it leads, you can prove something else that you know that's not true, that I know it's not true. So I'm convinced that PPAD is not NP complete, because Nimrod show way back that if that case called P equal NP.
So why is NP not equal to NP?
PPAD.
Yeah, why do you believe NP is not equal to NP?
No, I'm saying in my life, it's real. I have some set of things
Okay,
that I believe strongly.
I'll
So if
go
somebody
to
show me
PPAD
the So my question is, there something about that one that no?
No, probably not. But since the answer has to be very personal to you because it's a subjective question, then I'll try and convince you.
No, it's not. It's what's against everybody. It's not that strong.
Okay, I would be very surprised. So that's why I put it here. Anyway, so suggested reading. There is a paper called Continuous Local Search. So CLS should be understood in the context of PLS, which is very nice and defines a complexity class that's strictly within this, captures a number of interesting problems. No problems have been shown hard for this complexity class. This one is in it, this mixed hash of a polymetric coordination game. There are other problems in it, like finding a mixed hash and a congestion game. But actually, it's quite easy to see, though it doesn't feature in that paper, that you can reduce these polymetric coordination games to mixed hash and a congestion game. Okay, so if you want to try to look for an algorithm, maybe this is a place to look for it. If you want to look for a hardness result, then there are plenty of other problems in there that look a lot harder than this one.
Very wrong. So you said no problems are shown to be complete for CLS, or?
They have a canonical one that defines it, and they have another bunch of natural problems that they show in the class, but they don't show any of them are complete for the hard of the class.
Is there an LCP which is hard for PLS? Is it not some class of matrices?
Finding a pure, only if you restrict what solutions you're happy with. No, I don't know.
But that's not an LCP.
That's not LCP then, yeah. I don't know.
So that's not known.
Yeah, that's unknown, I think. I have to think about it. P-matrix LCPs in this class,
I know.
yes, though, as you probably know. Yeah. Okay, so let me briefly, very briefly, say what the results are here. So there is a line of work following the PPAD-hardness of ruling out FP-TAS for bimatrix games that has basically looked at what we can do in polynomial time in terms of constant epsilon. Aviad's result rules out even a p-TAS if you believe in the hardness of PPAD. So there may be, I mean, I still think it's interesting to look for algorithms that give good epsilons in polynomial time for polymatrix games, because perhaps they then give you equilibria too, for example. So yeah, there's a line of research that has slowly improved from a very trivial algorithm of Daskalakis method of Papadimitriou down to the gradient descent method of Saknakis-Varakis has got us down to epsilon 0.339, where 0 is a Nash equilibrium, 1 is nothing. This uses gradient descent, and for more players, the best we know in a general game is something that tends to 1 as n goes to infinity. So the result I want to highlight, but not really go into in detail, is a result of mine, John Fernley, Argyris Stilikas, and Hausdorff that gives a 0.5 plus delta approximate equilibrium in a polymatrix game that's polynomial in the input size and 100 delta. It extends this gradient descent idea and basically defines a combinatorial gradient on the maximum regret of the players. So the algorithm is rather simple. The proof a bit involved, but it basically starts from an arbitrary strategy profile, finds a direction to go with an LP that's basically working with a gradient, an approximate gradient, and then goes some distance in that direction and keeps going until you get something good enough. Okay, I need to wrap up. So there's a bunch of open problems related to these approximate equilibrium polymatrix games, but I'll skip that. And I'll skip this. So Bayesian games can be, so two-pair Bayesian games can be directly written down as polymatrix games. So perhaps with complete bipartite interaction graphs. So that's another natural type of interaction graph to restrict to for maybe approximate equilibrium or something. And final slide then. So there's some interesting work on solving general multiplayer games using polymatrix games as in an iterative way to improve, iteratively improve your approximation of the equilibria. There's some very nice work on zero-sum polymatrix games of Daskalakis, Papadimitriou, Yang Chime, and one other co-author. Guido's going to talk about efficiency of equilibrium polymatrix coordination games, and there's this QP-TAS for three polymatrix games. These are all relatively recent results, and there's some open problems related to all of them, so I hope you have convinced you that there's some, it's worth looking at polymatrix games. Thanks.
Question? One question.
So you mentioned one of your results that it's the PLS hard to find a pure equilibrium in a particular class of polymatrix games. Can't it possibly be the case that it's actually NP hard to decide the existence of a pure equilibrium in a more general class of polymatrix?
Yeah, very possible.
But nobody has shown that at this point?
I'm not sure.
Be surprised.
If it's not, I wouldn't be surprised if it's not. So I'm not sure if anyone's written it down. I mean,
so I mean, you know, you're showing PLS hardness. If I can get NP hardness for free,
but it's easy to verify that these are in this class. I mean, team polymatrix games are interesting in their own right.
I understand. So these are potential games, and therefore it's a different. Yeah, okay. But surely somebody must have.
I mean, I think even in two players, yeah, it'd be hard to decide.
It did. No, wait a second. For two, no.
If there is a pure, deciding if there is a pure equilibrium in a two-player game.
What do you mean?
How are you represented?
The whole point is that polymatrix games are succinct games, and therefore, you know, that's the whole point.
No, okay. I'll think of that. But yeah, it's still simplified. Probability.
Has somebody written that down?
He's professing.
I
don't know.
No, what it means for given support it's NP-hard, but not support of one, because that's maybe a one.
No, in
Well,
Polymatrix games.
Yeah. No, but saying it's not by bimatrix games.
Yeah, I think that's let's forget bimatrix games.
Well, that's just isn't it a special case of polymatrix?
No, I'm sure we could write this down. I have no idea if someone else has written this down.
Yeah. Okay.
Thank you very much. Yes,
Group photo outside.
Yeah. Yeah, I was looking for this board. Where did I leave it? On one of the tapes. Oh, we transferred it to the other computer at the last minute. No one got it. Right? Thank you. Yeah, I'll stop it. I guess that's the point. Well, as I said, the logic of it has evidence in mind. So this is a highly influential not much more. I mean, there is your strength. Yes. And this is not yeah.